Today is actually one of my favorite topics, parametric equations and parametric curves. Technically, it's the last section of chapter 4, but I'm also going to introduce chapter 5 while doing this last section of chapter 4. What's chapter 5 about? Chapter 5 is about definite integrals. And the very first section of chapter 5 is about trying to motivate the idea of a definite integral. If you know the speed, can you find the distance traveled? Is the question. Before, what we've done is, if you know the distance traveled, can you find the speed, right? Here's a function that gives you your distance traveled. You find the speed by taking the derivative. Or more generally, if you've got a function that gives you position, you find the velocity by taking the derivative. Okay? Now we want to go the other way. Integration is the reverse of differentiation. They are related to each other. But one key thing, and this is really the foundations of where calculus came from, is the realization that to do integration in this context, to take a speed function and find a distance traveled, instead of finding a slope of a tangent line, you find the area under the curve. It was that realization that was really the true birth of calculus. Let's start off with a simple example, relatively speaking. Parametric equations and parametric curves, the main application of these things is to basic physics of motion. You could call it kinematics, where you are describing motion with equations, as opposed to dynamics in physics, that's deeper subject, where you are using physical laws to try to figure out motions. Newton's laws, that kind of thing. F equals ma. We're not doing F equals ma here. We're just have a certain motion, like a bug is crawling across my piece of paper here, and I like to describe the bug's motion. Is it trig bug? Well, maybe. Remember trig bug? I'd like to describe the bug's motion with equations. I'd like to use math to describe the motion. And let's say the bug starts at this point, and just to be different, instead of going left to right in the usual way, let's go right to left. Let's say the bug travels from this point to this point. Where are those points? Well, let me just make up coordinates here. Let's say this point has coordinates. Oh, I'm going to try to make the numbers work out nicely here. 2, well, maybe 3, 1. 3, 1. I'd like to make this a nice right triangle here. So I'd like to make this height 4 and this, this one 3 and this one 4. And if that's the case, then the coordinates of this point better be -1, -2. So the bug is going to travel along that line. And I made this a 3, 4, 5 right triangle so that the numbers come out nicely. And the hypotenuse has length 5, right? 5 squared is 25 equals 9 plus 16. 3, 4, 5 right triangle. That'll make thinking about this nicer. How long does it take the bug to travel from this point to this point? I don't know. It's a very slow moving bug. Let's say it takes 10 seconds to travel from this point to that point. Maybe it's a flea, something really small, so it can't move very fast, or can fleas move fast? Maybe they can. So it travels from this point to this point in 10 seconds. Travel time equals 10 seconds. And let's pretend the units of distance are centimeters. Units of distance are going to be in centimeters. And you can see I've labeled the distances here. The question is, what are equations describing this motion? Question, what are equations that describe this motion? And the answer is, it depends. Well, what does it depend on? not a question mark, but exclamation point. It depends. But what does it depend on? Well, it depends on how the bug is moving. For one thing, is the bug speeding up and then slowing down and stopping to smell some roses and then going on its merry way for these 10 seconds? Or is the bug more methodical, traveling at a constant speed? What time does the bug start moving? Right now? What time is now? I guess 12:52 p.m. Is that time 0? It is if you want it to be. Right? We often, for the sake of modeling, choose the starting moment of time to be t equals 0. Why not? Keep it simple. These are all serious considerations to make. Yeah, well, let's say the motion is constant speed to keep it. That sounds most simple, right? So suppose it's a constant speed motion. To keep it simple. Maybe it's constant speed, maybe it's not. But just for the sake of simplicity, and maybe it's matching reality, assume this little flea is traveling at a constant rate. So it travels 5 centimeters in 10 seconds. One thing you could say about it is it's traveling at a speed of 0.5 centimeter per second, right? 5 divided by 10, 5 centimeters per 10 seconds. Of 5 centimeters per 10 seconds, 0.5 centimeters per second. But that doesn't really answer the question of equations that describe the motion. How do you come up with equations that describe the motion? Well, come back up to the picture here. What should I label these axes with? How about the usual x and y? Let's not book tradition. I've really got 3 variables here. These position variables, x and y, and also a time variable, call it t. In reality, as the bug moves, x and y are changing. They are both functions of t. And I hope it's intuitive that since the bug's moving at a constant rate, they're probably linear functions of t. If you graph them, it's probably straight lines. I mean, yes, this is a straight line, though if the bug's not moving at a constant rate, if the bug's speeding up and slowing down, x and y are not necessarily linear functions of t. But if it's moving at a constant rate, they're probably linear functions of t. I could try graphing them. 2 graphs. X is a function of time and y is a function of time. I'm trying to take the information in this picture where I'm imagining the bug moving over time and translate that to information in 2 separate graphs, x versus t and y versus t. Think about each coordinate individually. X is decreasing from 3 down to -1 as t increases from 0 to 10. And y is decreasing from 1 down to -2 as t increases from 0 to 10. X is going from 3 down to -1, 3 down to -1 as t goes from 0 to 10. The graph of x versus t, it's got to look like that. Y is decreasing from 1 down to -2, 1 down to -2 as t increases from 0 to 10. It's got to look like that. I'm hypothesizing that using straight lines is what I need to do here to make this a constant speed motion. Seems reasonable, right? That's probably the case. If you're traveling at a constant speed in this 2-dimensional plane, both x and y must be changing at a constant rate. These must be constant slopes. And they're negative slopes here because x and y are both decreasing. The bug is moving from right to left and also downward in this picture. By the way, in reality, if you're watching a bug move on a piece of paper, the coordinate system's not usually in the picture. You just see the bug moving on the paper. Where does the coordinate system come from? Well, you just got to impose it. You got to decide where the origin is, pick measurement units, and then figure out where the bug started and where it ended. I'm just pretending I've done it in such a simple way. In reality, with most bug motions across a page, it's probably not quite so simple. Especially if you're using standard units like centimeters and seconds, it's probably not quite so simple. So what are these equations? What are the equations of these graphs? Well, the slopes are constant and they're negative. They're rise over run. Delta x over delta t for this one. Change in x is -4, right? X decreases from 3 down to -1. As a difference, I would write that as -1 minus 3, -4. Change in t is 10, -4/10, which is -2/5 or -0.4. The slope of this one is really delta y over delta t, change in y over change in time. That's -3 over 10. -0.3. You call them slopes in the picture. You could also call them rates of change of x with respect to t and y with respect to t. They are constant. I can also see the vertical intercepts. For x is 3 and for y is 1. So x as a function of t, let's call it f of t, is -2/5 t plus 3, right? That's a t there. Slope is -2/5. Vertical intercept is 3. It's no longer a y-intercept, it's an x-intercept, where x is vertical in this picture. Don't let it confuse you that x is vertical in this picture, whereas x is horizontal in this picture. It's not a big deal. Okay, you can make axes any direction you want them to be. It's just, what are you used to? And here, y is some other function called g of t, -3/10 t plus 1. It's these two equations that are called parametric equations, depending on some parameter. T, time, is the parameter. That's a different use of the word parameter than I've done before when we were talking about families of functions that depended on parameters, like an a, that could be different values of a, or with the normal curves, there was a mu and a sigma that could take on different values. Those are constants when you graph those functions, though it's interesting to think about what happens when the constants change. We also did that with the project. Parameter here, t, is really more of a true variable. I do want to think about what's going on here as t changes, as time goes by. The bug is moving, described by these equations. This mathematical description of motion, again, is called kinematics. Again, as opposed to dynamics, which is deeper physical stuff involving Newton's laws. We're not trying to understand the motion in terms of Newton's laws. We're just trying to describe it mathematically using equations. And do note the derivative of this one is -2/5, slope of that one. The derivative of this one is -3/10, slope of that one. These derivatives, these functions have constant derivatives because they're linear functions. Together, this forms what you could call a system of parametric equations. I write it as a pair of equations like this. This is a system of parametric equations. Anytime you have a system of parametric equations where x and y depend on some parameter t, often representing time, this also generates what's called a parametric curve. What's the parametric curve? It's the curve traced out in the xy plane as t varies. It's that line. That's the parametric curve. Now it's a line, I'm calling it a curve. Well, lines are special cases of curves. Just like, squares are special cases of rectangles. Happens to be a line. In general, it could be some curve that's truly curvy, not just a line. But it's more than just the curve itself. It's also how the curve is traced out, what the actual motion is, in this case at a constant speed. It's possible the bug's not traveling at a constant speed. Then I would need different parametric equations. But the actual curve that you draw could be the same curve. It could be still starting here and ending there and traveling along a straight line. Even if these were nonlinear functions, that could happen. In fact, we'll make examples where that does happen. Can I clarify anything? It's also important to realize some other perspectives on this. We can represent it as what you could call a point-valued function. Point-valued function. I typically call these point-valued functions C of t. Why? I don't remember. It's x comma y, where x depends on t and y depends on t, by the equations that I wrote down. X is 2/5 t plus 3, and y is -3/10 t plus 1. What do I mean by a point-valued function? I mean the output of this function is a point in the plane, a two-dimensional object. Well, okay, it's a point, which is a zero-dimensional object, sitting inside a two-dimensional plane. It's got two coordinates. These are rectangular coordinates here. Rectangular coordinates, the ordinary Cartesian or rectangular coordinates of a point in a plane. By the way, when you got rectangular coordinates, or when you got ordered pairs like this, two numbers separated by a comma inside parentheses, we're used to thinking of those as rectangular coordinates, x and y, but it doesn't have to be rectangular coordinates. It could be some other coordinate system, like polar coordinates. And in Calc 2, you will learn a little bit about polar coordinates, and for sure in multivariable calculus. What are polar coordinates? Well, you got an ordered pair where the first coordinate, instead of being called x, is called r, and represents the distance to the origin. And the second coordinate, typically called theta, represents the angle that the point makes, well, the line through the origin to the point makes, with the positive x-axis, an angle, r theta, polar coordinates. Because it's kind of like when you make the grid for it, it's kind of like you're looking down on the surface of the Earth, looking down on the North Pole, and you're looking at lines of latitude and longitude. That's why it's called polar coordinates. You see lines emanating from the origin and circles centered at the origin. The circles tell you how far you are from the origin, and the lines emanating from the origin tell you what angle you're making with the positive x-axis. There's not, and there are other coordinate systems as well. If you take differential equations with linear algebra, we talk about slanted coordinate systems, of all things. And it's important. Slanted coordinate systems, yeah, where the axes are slanted with respect to each other. Yes, that's important. Why? It's helpful for problem solving. I'll just put it that way. The coordinate system you use depends on the application. We're used to rectangle. Okay, we'll keep it with rectangular. So I could think of the output as a point. For any input t, a real number, I get a point. I could also convert this to a vector valued function. I could use the exact same notation. However, it's somewhat traditional to use different notation. Somewhat traditional to use R with a little funny thing above it. What is that? That's a half arrow. It's supposed to represent a vector. What is a vector? Some of you know what vectors are and some of you don't. Okay, in physics classes, vectors are just arrows. They're quantities that have a magnitude, which is the length of the arrow, and a direction. Okay, there's a vector. There's another vector. They're different vectors. They have different lengths and different directions that they're pointing. When you see vectors written in books, they're typically written with boldface notation, but it's hard to write boldface notation with chalk or pencil or pen. So we typically make little arrow symbols above it, but we get a little lazy and just put a half arrow just because we're a little lazy. Seriously, it's just a little quicker. I make my arrows that way. Other professors make their arrows go backwards. Which one's right? It doesn't matter. Some even put their arrows underneath instead of on top. It's weird. Very inconsistent notation with vectors. Anyway, there's also something called I hat and j hat notation. You could write x I hat plus y j hat, which is f of t times I hat plus g of t times j hat. What in the world are I hat and j hat? And yes, you'll put a little hat above them. Actually, some people put little half arrows. Such inconsistent notation. It's confusing, so inconsistent. Kind of just depends on what you like. I hat is an arrow that points straight to the right and has a length of 1. Pretend that's 1 centimeter. And j hat is an arrow that points straight upwards and also has a length of 1. But wait a minute, what's straight to the right and straight up? I mean, if I turn this, then it's no longer straight to the right and straight up. Well, it depends on your frame of reference. Okay, pretend you're looking at it so that, okay, that basically looks straight to the right and straight upwards. They're called the standard unit vectors. I hat pointing straight to the right with length of 1, say 1 centimeter. J hat pointing straight upward with the length of 1, say 1 centimeter, just to be something specific. But it could be different measurement units. And it turns out that an arbitrary vector can be written as some multiple of I hat plus some multiple of j hat by what it means to add vectors. I'm not going to get into details. This vector would be f of t times I hat. Pretend t is some fixed number. And this vector would be g of t times j hat. Essentially, I've taken I hat and j hat and scaled them by some scaling factor. And then if you combine them in this kind of picture with a rectangle here, this is the resultant vector. This is the R of t. I don't want to get into details of why in the world you would do this. It is related to applications in physics. I'm just trying to inform you about it. To tell you the truth, when we do this kind of notation in math classes, we actually, for the most part, avoid I hat and j hat. We could write point notation, but we also, to distinguish it from points and emphasize vectors are arrows, is use something different than parentheses, like maybe pointy brackets, like this, f of t, comma, g of t. Weird, 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 okay? You just got to get used to it and realize it's weird. I'm serious. Don't let it bother you. Yes, it's inconsistent. But yes, you do need to be informed that different people use lots of different notations here. Actually, it gets even wilder. People use other notations besides this. Some people use square brackets, and then it gets confused with intervals. Some people use column vectors, a 2x1 matrix for these, where to put these things. In fact, I do in diffie-q with linear algebra. Why? Because it's just more convenient in that class. Why? I'll wait till you take the class to get into why. Don't let it bother you. Maybe feeling pretty confused right now? Don't let it bother you. I'll try to make this stuff more clear now by doing Mathematica. Really? Mathematica will make it more clear? Well, hopefully. Let's put this example into Mathematica. This will be worth doing. Let me define my f of t and my g of t. F of t is negative 2t over 5 plus 3. G of t is negative 3t over 10 plus 1. I'm also going to define c of t, or maybe I should call it r of t, actually. In Mathematica, though, if I do this, I don't want to use parentheses or pointy brackets like I did on paper, because Mathematica would interpret those incorrectly if I use parentheses. These are just programming details to know. Instead of Mathematica, you want to use curly braces. F of t, g of t, like that. If I do this in Mathematica, is Mathematica thinking of r of t as a point or an arrow? The answer is it depends. It depends on what plotting command you use. What I want to do now is I want to graph this. The most basic thing to do is to use something called parametric plot. You can do this on your calculator too, in parametric mode on your calculator. Maybe some of you have done it, maybe some of you haven't. Let's do it real quick on the calculator, then we'll come back to Mathematica. Parametric mode in your calculator, if you go to the mode screen, switch from func to par, like that. That's on my mode screen. So you got to go to your mode menu. Maybe yours looks different. But if you go there, you should see an option for function versus parametric, func versus par, maybe. And if you do that, if you enter the par and then go to the y equals screen, it looks different because you're in parametric mode. You want to plug in both x as a function of time and y as a function of time. Negative 0.4, if you press your variable button, instead of an x, it's a t. Plus 3, and then go down to the y, negative 0.3 t plus 1. So go to first the mode, switch to par or parametric. Go to your y equals screen. You should see something like this. Plug in these functions. X is a function of t and y is a function of t. I just plugged my ordinary variable button to get the t. Same as the x button. For the window, you'll see a t-min and a t-max. Let's see, the bug is traveling from time 0 to time 10. You'll see a t-step, pick 0.1. You'll see an x-min, x-max, a y-min, and a y-max. We're trying to watch the bug move here. We probably better pick a window like maybe negative 5 to 5 in both directions. Like that. X scale and Y scale 1, maybe to make my tick marks 1 unit apart. Okay, I'm about to hit graph. And what are we going to see? We're going to see that line. And it is going to be traced out, watch it, from right to left, not left to right. Because that's the way the bug moved. And it'll be traced out at a constant speed. Watch it here. Ready? 1, 2, 3, go. Zoom. There. Well, that was faster than 10 seconds. How can I make the bug go slower? If I make my t-step smaller, like 0.01. Then it's going to plot more points and it'll get traced out slower, 10 times slower, in fact, graph. Yes, now the bug's moving very slow, and maybe it'll take about 10 seconds to travel this entire distance there. Maybe even slower. Okay, you see it moving at a constant speed at the right starting point and the right ending point. Okay, so that's a quick showing you how to do it in the calculator. What's going to happen in Mathematica? Well, initially with parametric plot, the answer is it's not going to be as ideal as the calculator. Here's the syntax for making a basic parametric plot. Notice I got the capital P in 2 spots. And there it is. That's the curve, but where's the motion? We don't see it traced out. We see the finished product. We want to know about the motion. So to actually get a motion in there, you need to embed this in a manipulate. Remember the manipulate? Makes animations. Going to copy and paste this code into the manipulate and let my right endpoint be a variable that I usually call b because it represents the right endpoint of an interval. And then put a comma, b going from 0.001, say, to 10. I have to pick something slightly bigger than 0 to start with there. Because if I put 0, it'll say mistake. Because it can't plot from 0 to 0. And it'll also be nice to fix a plot range. Plot range, say -5 to 5 in both directions. This is the syntax. I'm not going to explain it. I will make this Mathematica notebook available. If you're interested in playing with it after class, it's not going to be required. Now I've got a slider that I can play. And there's the motion. Although it's not as ideal as the calculator, it's kind of herky-jerky. It's meant to be a constant speed. Hang with me. It is worth doing the Mathematica still here. And it plays it over and over again. You can slow it down or speed it up if you like. I'm slowing it down. Let me also make it a little darker so it's easier to see. Plot style. Pick. Yes, 0.01. Red. We'll make it thicker in red. Easier to see. There you go. It's also worthwhile to add on to this picture, to add what's called a position vector. That really is what we just saw is the point moving. That's the bug's motion. It's also handy to add a position vector to the picture. I'm going to write Mathematica code very quickly. You don't need to know the details of this code, how this works. Let's see here. Be careful. I'm using a graphics command called arrow that's going to draw in a position vector of the object as it moves. And I guess I need to keep the origin in the right spot. Axes, origin, 0, 0. Okay, so this now is not only showing the motion of the bug, which is the red line, but also an arrow starting at the origin and always pointing at the location of the bug. That's the position vector of the bug. If you ever take class like mechanics in physics, this is very, very important for you right now. I suppose mechanical engineering majors need to take mechanics. You're going to deal with this kind of thing all the time in mechanics. It's called a position vector. It's kind of fun. It's like a blue pen is tracing a red curve. Maybe I should make them both blue. That would be more conceptually nice. Here's something else. I can also add a velocity vector to this picture. What's the velocity vector? It's the derivative of the position vector. What else would it be? How do you differentiate it? Velocity vector. Call it v of t with a little half arrow above the v. That's the derivative of the position vector. And I'm just going to use this notation. You find it by differentiating the f and the g, the so-called components of the position vector. That's also an arrow, or it can be visualized as an arrow. Where? Where should you visualize it as an arrow? And what does it equal? Well, it's a constant vector. If you differentiate f, you get always -2/5, and if you differentiate g, you always get -3/10. It's a constant vector. So it always, if you draw it, it always points to the southwest here. Its two components are two negative constants. This is -0.4, and this is -0.3. Now, of course, those lengths are positive numbers, but because the arrow points to the southwest here, down and to the left, I think of the components as being negative. It's not that the distances are literally negative. It's convenient to keep track of direction. Yeah, first component -0.4, second component -0.3. It's pointing in the direction of motion. This arrow is parallel to that line. And its length is the speed. Very key. Its length is the speed. The speed is the length of v of t, which is constant here, and it can be found with the Pythagorean theorem. Square root of -2/5 squared plus -3/10 squared. That's square root of 4/25 plus 9/100. If you get a common denominator of 100, that's 16 plus 9/100. Square root of 25/100 is square root of 1/4 is 1/2 centimeter per second. Where have we seen that number before? Right there. We already knew the answer. That's the constant speed. It's the length of the velocity vector. All this stuff generalizes in some really cool ways. Hang on here. Take a breath. That's the speed, that's velocity vector. I can put it in this picture by adding another arrow. Let's make it a red arrow. Again, don't worry about the syntax here. I got to make sure I get the syntax right. Let's make this even thicker, a thicker arrow. I think this will work. So you see the blue arrow pointing from the origin to the location of the bug at time 0. You also see a small red arrow. That small red arrow stays the same direction and same length as the bug travels. It's representing the velocity vector. It's a constant velocity vector as the bug moves. Its length is the speed. It's a pretty short arrow because it's not moving very fast. Its length is 0.5. You could also, if you wanted to, figure out an acceleration vector. Differentiate the velocity vector. What would you get? Well, this is a constant function. You'd get 0, the 0 vector, which is just a point. The acceleration is 0. This is constant velocity. Not only is it constant speed, but it's also constant velocity. In general, the acceleration is not 0. All right, now we're quickly going to generalize this. And Mathematica is going to make this very easy. What if I change the motion to something else? What if I made a new function, call it R1 of t, that is R of, always say, t squared? I'm I'm making a new vector valued function that takes the old one and replaces the t's with t squared. What is the formula for this? It's the exact same formulas, except the t's are replaced with t squareds. The motion of this is still along a line. The same line, in fact. X and Y are still along the same line. How do I know? And what is the line anyway? What's the XY equation of this line without t? Is it possible to eliminate t? Yeah, it's called eliminating the parameter. Let me come back to these equations. I could take, for example, this equation and solve for t as a function of x. Solve for t in terms of x, find its inverse function, really. First by subtracting 3 from both sides, and then multiplying both sides by negative 5/2. And then I could plug that into the other equation in place of the t and get y is negative 3/10 times negative 5/2 times x minus 3 plus 1. Careful not to make a mistake. Multiply those fractions. You're going to get positive 15/20, which is the same as positive 3/4. X minus 3 plus 1. 3/4 x minus 9/4 plus 1 is y equals 3/4 x minus 5/4. A line with a slope of 3/4 and a y-intercept of negative 5/4. That's what this line is if we weren't thinking about motion. The slope of that line is 3/4, positive 3/4, and the y-intercept is negative 5/4. We eliminated the parameter t to find the xy relationship of this line. It doesn't tell you what the motion is, though, because the time has gone away. If I go back to these equations and replace these t's with t squares, I get a different motion, but the line is still the same, because if I replace that t with a t squared and solve for t squared, I'll get t squared as that. And then if I could replace the t squared there with the same thing, I'll get the exact same calculation. It'll be the exact same line, but because t is replaced with t squared, the motion itself is different. It's not a constant speed motion anymore. So what is it? Oops, that's not Mathematica. Well, let's copy and paste this stuff here, and let's change the R's to R1s. Let's also change the amount of time the bug travels from 10 seconds to, how about square root of 10 seconds? Because we replace t with t squared. If the bug's going to start and end at the same point, and I replace t with t squared, I better go to square root of 10 instead of 10. Square root of 10, which is a little bit bigger than 3. Watch the motion now. Watch it carefully. It's no longer constant speed. That red arrow is getting longer. The bug's speeding up. But it still starts at the same place and ends at the same place. Starts at the same place, ends at the same place. Speeds up. Now 0 to, not to 10, but 0 to square root of 10. Total distance traveled is the exact same thing, though, 5. The average speed is still 1/2 centimeter per second. It's very slow at first, then it speeds up. Can I graph the speed? Can I make a function speed of t? What's speed of t? Well, it's a constant function in the first case, just 1/2 centimeter per second, but maybe I should type it in the more general form. And this is something to write down if you haven't written anything down yet. The general formula for the speed, hopefully you've at least written what I've written, is square root of f prime of t squared plus g prime of t squared. It is the Pythagorean theorem. It's the length of the velocity vector. And with this example, the first example, it is constant, 1/2. And if you plot it with an ordinary plot, its graph's a horizontal line. And guess what? The area under that line is the distance traveled. It's a rectangle. Base is 10, height is 1/2. Base times height, 10 times 1/2 is 5. Yeah, the bug went 5 units of distance. This is hinting at integration. You integrate the speed, you find the area under the speed graph, it's the total distance traveled. Well, it's very easy here because the area is a rectangle. But what if the speed's not constant? Oh, I didn't do an F1 and a G1. Okay, F1 of t is f of t squared, and G1 of t is g of t squared. Those are no longer constant functions. And the velocity vector, which I've already typed in as R1, the position vector is R1, the velocity vector, the derivative is no longer constant. These are no longer linear functions, they're quadratic, and this is no longer a constant function. That's the velocity vector for this increasing speed motion. What's speed 1 of t? It's this, same formula. Is that a constant function? No, it's square root of t squared. What's square root of t squared? T, when t is positive at least, in general it's the absolute value of t. If you plot speed 1, t goes from 0 to square root of 10, you get a line with a slope of 1. Area under it's the area of a triangle. 1/2 base times height. 1/2, what's the base? Square root of 10. What's the height? Square root of 10. Square root of 10 times square root of 10 is 10. Times 1/2 is 5. 5 units of distance. The area of the triangle is still the distance traveled. Generalize this one more time. What should I do here? What should I do? How about, okay, let me just type it quick. How about replacing t with t cubed? Oops, and change the 1s to 2s. Hang with me, this is really important. Speed 2, it's a different motion, but it's the same line here, still starting at the same place, ending at the same place. Square root of f2 prime of t squared plus g2 prime of t squared. Okay, what is speed 2 of t? It's 3/2 square root of t to the 4th, which turns out to be 3/2 t squared. Is the area under that graph still 5? Yes, as long as I pick the right endpoint, it's no longer square root of t, it would be cube root of t, or 10, excuse me, because I replaced t with t cubed. But the graph is, oops, speed 2. The graph is no longer a line, it's a curve. How do you find the area under a curve? That's what integration is all about, and the fundamental theorem of calculus. How can you get Mathematica to do it? Use an integral button. Integral, but this one's called the definite integral. I use this button here that's got a lower limit of integration, that's starting time 0, and an upper limit of integration, the ending time cube root of 10. I integrate the speed. This looks just like indefinite integrals, except you got these numbers on the top and the bottom. This is going to give me the area under the curve, and it should equal 5. Yay. How do you find it without a computer? You use the fundamental theorem of calculus. You do an indefinite integral first. You find an antiderivative of effectively 3/2 t squared. You plug in the upper limit and subtract what you get when you plug in the bottom limit. I don't expect you to remember that right now. Talk about it more on Friday. That's the fundamental theorem of calculus. That's Newton and Leibniz's greatest mathematical discoveries. That is the birth of calculus, realizing you could do that to get the answer for the area, and it solved the practical problem. We're out of time. On the problem solving videos, I've got other examples like circular motion, and that'll come up on homework, and even non-straight line, non-circular motion with other parametric equations. But I've hit at the heart of the main ideas here with this example, these examples. Have a good day.